Okay, now a quick recap. Your equation of the internal energy, U is 3/2 NKT. Okay, so from here you have understood that internal energy is proportional to temperature, and then temperature is also proportional to the kinetic energy. This is given by the equation 3/2 kT is half mc squared. This equation here. Okay, we derived this one the other day. All of these are constant. This is kinetic energy, so temperature is proportional to kinetic energy. So this is our conclusion. Now, so if I can increase the kinetic energy, which is the speed, the mean square speed, then I increase the temperature, then I increase the internal energy. Double this, double this, double this. Okay? So now there are two ways. If I want to increase the internal energy, number one, remember we are trying to increase internal energy. So that means you are trying to increase the kinetic energy also. Since kinetic energy increase, internal energy will increase. So two ways. Number one, from your thermodynamics equation. These two ways you got from your thermodynamic equation. Delta U equals to Q plus W. Now, let's talk about the first one. Is add heat to the system. Q. You will produce delta U, right? So add heat to system. So when you add heat, you have to make sure that when you're heating it, you do not move the piston. You do not let the gas expand. Initially, the gas moves at velocity v. Then I hit it, you will see the speed start to increase only if you do not allow the gas to expand. Why? Because if you let the gas expand, the speed will be affected. You have to also remember this. If gas expand, if the gas is allowed to expand, if you give it more volume, then their speed will decrease. And thus kinetic energy will also drop. So in the end, we are increasing the kinetic energy, right? So it's important that when you add heat into the system, you do not let it expand, so your KE overall will increase. Then you will have an increase in internal energy. Okay, this one, right? Careful with this one. When you change the volume, that will affect the kinetic energy. So this is number one. So plus Q. Add heat is plus Q, remove heat is minus Q. So number two. Number two, from your thermodynamics, again, work done. So work done on the gas will also increase the kinetic energy. Okay, so when you do work on the gas, so you are compressing it. Here, you compress to a smaller volume. Again, I make sure when I compress the gas, I do not add heat or remove heat. Let's just keep the Q constant. Okay, keep the Q constant. I just increase the volume. So I have to do it slowly, because when I do it very fast, the friction will give you extra heat. If I suddenly press very fast, then the heat will be generated from the friction, extra heat. Now your Q is no longer constant. So I do it slowly like this, work done on the gas. So here you see that the speed will also increase. So overall, I'm still increasing kinetic energy, then the internal energy will increase. So this is your two ways to give you a positive delta U. Now, also remember, positive work, positive W is work done on gas. If you have negative W, is work done by the gas, meaning that the gas pushes the piston outward. The gas is pushing, so it is doing work on the piston. In that case, you will get a minus W. So overall, whether it is increase or decrease in internal energy, you are comparing these two quantities. Who is bigger? You can have positive W but negative Q. What does that mean, positive W and negative Q? Meaning that you're doing work on the gas while you're losing heat from the system at the same time. So who is bigger, that will determine the internal energy is increase or decrease. Okay? You can also add heat into it, but then you have a minus W. Add heat into it, minus W. So if you add heat to it, just like the equation, the step number 1, if you add heat to it, positive Q, and you let the gas expand, it's a minus W. That will cancel out, give you a 0 delta U. So the temperature doesn't change. Now, this is related to temperature. Remember this one? Back to the first one. U is proportional to T to kV. If your temperature doesn't change, your delta U will always be 0. If your temperature doesn't change. So your delta U is linked to temperature. Please remember that. Also, a gentle reminder that temperature is not the same as heat. Q is the heat, is the energy you add or you remove. Temperature is not heat, temperature is temperature. That is measured by the internal energy. Okay? You add heat, this tells you one important thing. If you add heat, does it necessarily mean the temperature will go up? If you add heat? No. So you better be careful with that. When you add heat, positive Q, your temperature pressure not necessarily will increase. Because there's work done also. If the gas is doing work, then your temperature can stay the same, which is your internal energy stays the same. Okay. So I make a note here. Adding heat does not necessarily mean temperature will increase, because work can be done by the gas. Okay, now next one is your gas laws. Gas laws, this is how you remember it. PV equals to nRT, right? So N and R is a constant. We do not change the mass, we use a closed container. So I move the T over here, PV over T equals to constant. Now, PV over T is equals to constant. This one is boils. BO1 LE as Boyle's law is the PV. And if I do the diagonal, this one, this is pressure law. And if I do this diagonal, this is Charles. So for Boyle's law, it's just PV, right? So PV equals to constant. That means temperature is constant. This is what you get, Boyle's law. Since only PV in the equation, you see the Boyle's law, only PV is in the equation. T, we drop it. That means T is a constant one. The one that is not included in the equation is the constant one, the one that is kept constant. So Boyle's law PV, T is not in, so T is constant. This is how you remember it. If you see pressure law, now this one, okay, let's do Charles first. Charles law. Charles law. In the equation is what? Charles is VT. T is not included, so P is the one that is constant. Okay. So V over T equals to constant. Pressure is constant. And then the third one is pressure law. The pressure law is P and T we take. We don't take the V, so V is the one that's constant. P over T equals to constant. So volume is constant. Okay, so the relationship you can say T and V. If I bring V over there and P is inversely relation with V. Charles law. Charles law is V. You bring the T over there, so V is directly proportional to T. Again, this one you bring it to the right side. T is proportional to T. All T should be in Kelvin. Again, I remind you, all T should be in Kelvin. Okay, that's the ideal gas equation. Ideal gas equation. What about the first law? First law equation. Okay, the first law in Boyle's law. Delta U is Q plus W. Temperature is constant. So remember, temperature is internal energy. They're all proportional here, right? So temperature constant, U must be constant. Okay. So if U must be constant, delta U is 0. There's no change in the U. Then minus Q equals to this, or I make it minus W equals to Q. This just means that if added is used by gas to do work. Okay, so positive Q, you add it, is equal to negative W. The gas do work. And one more row, you leave one more row for the PV curves. Okay, the PV curve, very important. You will most often see it, right? So the PV curve for Boyle's law. P against V. How's the PV curve? Then you see from here, P is inversely to V. So this is an inverse graph. Okay, so from the ideal gas equation is where we get the relationship. So the graph is an inverse relation. It's a curved graph dropping like this. V1, V2. So this line is one temperature. So let's say 300 K. let's say I got another curve here. This curve is maybe 500 K CD. The constant temperature from A to B, or the other way around, they happen in same temperature. Okay, now second one, Charles' law. First law equation. Delta U equals to Q plus pressure is constant. Pressure is constant. Okay. That means temperature is changing. Internal energy may change. Q also we don't know whether it's heat is absorbed or released. This one you have to see from the question whether heat is absorbed or released. We don't know. But we know the W. The W can be expressed as work is done, can be expressed as pressure times into change in the volume. This is from your formula of the work done. Work done by gas is pressure times into change in volume. This formula we use. Work done by gas. So let's say before volume before V1. Volume after gas push it. So increase in volume. What's the change in volume? Times by the pressure is the work done. Okay. Now this one. This V can be expressed with this. So this becomes the first law equation. Okay, so whether heat is absorbed or released, we don't know. We don't have information on that. We don't have information on this one either. Okay. PV curve. Constant pressure. Constant pressure, it will be a straight line. Here, B or C line. Okay, so from B to A, volume decrease. What does that tell you? Volume decrease. That means you are doing work on the gas. You increase the volume, you press the piston. How much work you've done on the gas? Here is delta V. This is P. So basically the area of the graph is the work done on the gas. The area under the graph. So P times delta V. That is work done. The area under the graph is work done. If I go from C to B, my volume increase. So gas is doing work on the piston, volume increase. From here to here, this area is the work done by the gas. Okay, so not until here, it's until the x-axis. So you can see the work done by the gas is bigger than the work done on the gas, which is what we want. In the engine, the jet engine, we put work on the gas, output must be bigger than the input. That's the point, like this. Okay. Last one, third one, pressure law. First law equation. If volume is constant, that means there is no work done. No work done, then delta U, whatever heat you put in will increase the internal energy. Whatever heat you take out will decrease the internal energy. Okay. PV. Constant volume, straight line. AB. Okay, going down. Okay, increase or decrease. Give me 1 second. Okay, so from A to B, there's no work done, constant volume. The pressure decrease. Pressure decrease. No work done, pressure decrease. And from C to D, pressure increase. Again, no work done. Which one is the heat being added? Okay, you can see from here to here, pressure increase. This must be the one that is heat added, plus Q. Okay, because plus Q, temperature will rise, pressure will increase. Plus Q, this is minus Q. Okay, just an example here. Did you bring your last worksheet that day? We look at maybe 2 questions before we continue. I said it in the group. You can refer to that. I just want to look at 2 questions, yeah. Okay. The worksheet thermodynamics for the online students. Okay. Now, Question 4. Question 4a, state the first law of thermodynamics and identify the meaning of any symbols that we use. Okay, so delta U, W plus Q, where delta U is change in internal energy. W is defined as work done on gas, and Q is heat transfer. The system. Okay, B, the state of an ideal gas is continuously changed according to the cycle. Okay, you see the diagram, it's in a combination of Boyle's law, Charles' law, and pressure law. Complete table 3.1 for changes A to B, B to C, placing 2 ticks in each row. Okay, let's look at A to B first. Change from A to B. It's what law is that? You see A to B, the volume drops and it is at constant pressure. That is the Charles law. Constant pressure, volume drops. That means I'm doing work on the gas. Okay, I'm doing work on the gas. Okay, what can we know about the change in internal energy? You have to take decrease, no change, or increase. What is the change in internal energy? From A to B, we can see from here, V is proportional to T, right? So from A to B, this is Charles' law. Charles' law, that means V is proportional to T. Since volume decreased, that means temperature must decrease from A to B, the volume drop. B. So the temperature must drop. So temperature must drop, and temperature is internal energy. So change in internal energy, decrease. Okay. So you take decrease, the change in internal energy. Again, is related to temperature. What about the work done on gas? Negative, 0, or positive? It's a positive. Work done. Okay. That is from A to B. Because the volume drops. Okay, B to C. B to C is constant volume. Okay, what is the change in internal energy? Yeah. From B to C, that one is pressure law. Look at the relation. P is proportional to temperature. So you see pressure increase, temperature also increase. Temperature is proportional to, again, internal energy. So internal energy must increase. Tick increase. And the work done is 0 work done. Okay, next one. Use the first law of thermodynamics to describe and explain the energy transfer associated with one complete cycle. So you want to explain the energy transfer from A, go back to A, the whole cycle. They say explain energy transfer. Basically, it's explaining your first law because your first law is all energy. Internal energy, heat energy, work done is also energy. So it's basically explain this one. So from the whole cycle, what can you say about the whole cycle? Okay, we go one by one. What can you say about the W? If you look at the whole cycle, A, B, C, what can you say about the W? Is there W here, BC? No. AD, no. Is there W here? Yes. And the W here is area under graph, right? It's smaller than the W for the CD. So you talk about that. You talk about this one. The work done on gas is less than the work done by gas. Okay, what can we say about internal energy? The whole cycle, consider the whole cycle. The whole cycle, you start from A, you go back to A. You go back to the initial state. So the change in internal energy is 0. Overall change in internal energy is 0. Because you go back to the same state. And what can you say about the Q? If the overall change is 0, that means 0 equals to Q plus Q minus Q. Sorry, this one should be minus W, right? Because your gas is doing more work than you do it, you done on it. So the W net is the minus. Then we bring minus Q equals to minus W. Q is equals to W. This is a positive. That means heat must be added for this to be possible, since it is a plus Q. Heat must be added. Okay, question 5. Fixed mass of ideal gas is initially at temperature 17. The gas has a volume of 0.24 and a pressure of the all given. Pressure, temperature, and volume. State what is meant by ideal gas. It's always the same answer. Gas that obeys PV proportional to T. Don't forget the last one, where T is thermodynamic temperature, meaning it's Kelvin. calculate the amount N of gas. Mole. Okay, next one. Okay, so you have the gas cycle. Let's read the sentence first. The initial state is represented by point A. The gas is cooled at constant pressure to B. Okay, and then they say there's a removal of heat, right? 48.0 kJ. Then the gas is then heated at constant volume, go up to point C. And finally, the gas expand at constant temperature back to its original pressure and volume at point A. During this expansion, work done is also given. The gas does 31.6 of work. Okay, show that the magnitude of the work done during the change AB is 19.2. During the change AB, where's AB? Okay, AB is the horizontal line. Basically, they ask you to calculate the area under the graph. Okay, D1. W equals to pressure into change in volume. So you get the area under the line AB. One nine two zero. Okay. 19.2 kilojoule. Right, now this one probably is the most famous question in heat. Okay, you see this a lot in the past year. Okay, so we'll try one question here. how to do question like this, huh? Okay, complete the table to show work done on the gas, thermal energy supply, and also the internal energy. So let's start with AB. Now, this is basically W. This is the delta U. Sorry, this is the Q. This is the delta U. AB, work done on gas. That's the answer you get from the previous question. 19.2. Okay, they want all unit in kilojoule. Huh? So that's the work done. Is it a positive or negative? Work done on the gas. Positive, right? Positive 19.2. So you can easily get the increase in the internal energy. Just do your calculation. From A to B, delta U W plus 2. When you calculate, make sure you include the sign. So this is a plus 19.2 minus 48, which gives you minus 28.8 kilojoule. Minus 28.8. Okay, then we try BC. Now, what we can get from BC? From B to C. From B to C is going up vertically. No change in volume. So W is 0. If I put it in the equation, W plus Q, this is 0. So we got change in internal is equals to Q, but we don't know what's the value. We only know they're equal. Right, and it's not given any value here. Oh, we know this, right? We know that this is 0. Put down on gas from B to C. There's no change in volume, so it's 0. And then what do we know? What else do we know? This is equal. These two are equal, but we don't know what's the value. Okay, let's put it aside first. Let's put it aside first. We try this one. Okay. So if you don't know, then you do the other one first. Later we get back to that. Okay. So CA plus from C to A. From C to A, we are given work done on gas. And also C to A, okay. We also know C to A is constant temperature, right? C to A is constant temperature. That means constant temperature. That means the internal energy is 0. The change in the internal energy is 0. It's 0. W is minus 31.6 plus Q. So Q is 31.6. For those who are looking at the recording later, it's a bit blurry. Yeah, I'll try my best to get the clearest for you. Thirty-one point six. Okay, this is 0, and then this is 31. Okay, now we are left with the last two. How much is the increase in internal energy of the BC? Okay, to find this one, you look at the overall process. Remember the overall process, the internal energy must be 0. If you consider the whole process from A to B to C back to A, the overall process, the change in the internal energy is 0 because you come back to the original state. So that tells us that this will be positive 28.8. That's how you get 0 overall. So from A to B, your change is a minus. From B to C, your change is a plus. That's the only way you get the total is 0. Okay? So this will be equal to this one, but positive. Then you calculate the final Q. Oh, we know this is the same, right? This one is the same as this one. So this will also be positive. 28.8. Okay, total process, internal energy change is 0 because you go back to the same condition, the same state of the gas. So 0. If A to B, your internal energy decrease from B to C, which means your internal energy must increase because from C to A, there's no change. So overall, you will get 0. Okay, that's how you solve it. Like this. There are many types of question like this. Sometimes, okay. But slightly different. Sometimes they give you this different situations, but the way to solve it is the same. Okay, in the end, it's still your first law of thermodynamics, and combined with your gas laws, the Boyle's law, pressure law, and Charles' law. Okay, guys, we do a short break, 4 minutes. Then we continue to the second part. Okay, let's continue now. The heating capacity, okay, SHC. What is it? Now, put it simply, it is the thermal energy needed to change the temperature of a unit mass by 1 degree Celsius. When you define it, keyword is the unit mass and unit temperature. You have to mention that. Also, you have to mention the energy used to change. Okay. The thermal energy needed to change the temperature of a unit mass by 1 degree Celsius. So meaning, if let's say I got a beaker of water, initial temperature at 25, I want to bring it up to 26. just by 1 degree Celsius. This is 1 kg water. How much water, how much heat I'm going to need to bring it up by 1. We found this number, Q, to be 4,200 joule. Q is heat energy, right? So positive Q, you put in the 4,200, which is quite high, the value. Just increase by 1 degree Celsius for 1 kg only. If I want to decrease by 1 degree Celsius, 24. Same, I'm going to need to release Q4200. Okay, so it not only works in the increasing temperature, also works when cooling. During the cooling also works. So if you want to drop by 1, you're going to remove this much. Same. Okay, so that is specific heat capacity. From your equation, Q equals to mc delta T. Q is the heat you need. You can see this is your specific heat capacity. So for water is 4,200 J. Okay, express as J kg minus 1 degree Celsius minus 1. Sometimes you also see J kg minus 1 Kelvin minus 1. It's actually the same thing. Doesn't matter the degree of Kelvin. Okay, so meaning that 1 kg and 1 Kelvin, you're going to need that amount. So for M mass, and for how many temperature you want to increase it, you times by the specific heat capacity, you get the total you need. So let's say this is 5 kg. I got a water that is 5 kg. I want to bring it from 25 to 30. Okay, how much is the mass? 5 kg. So I will take the specific heat capacity of water, 4200 joule per kg, degree Celsius. Take that, you times into how much mass you are heating? 5. You times by 5, because this is just 1 kg. You times 5, 5 kg. And also this is just 1 degree Celsius. Now you got 5 degrees Celsius. You times into, again, 5. So this expression gives you what? This expression gives you the total energy needed. Okay, again, the energy you need per kg and degree, you times into how much kg you are heating, how much degree you are heating, that's the total energy you need. So that's where we get this expression. C M delta T, big Q. Q equals to MC, MCT, this one. Okay, so make sure the Q you know, okay, it is the energy required, energy I put in or released, can be released also. It's given by this one. Okay, now example. Example of calculations. Let's say I take 2 water, okay? One is 50 grams at 100 degrees Celsius. H2O. I'm going to mix it with a 200 gram of same H2O, but at 10 degrees Celsius. Can you calculate the final temperature when they reach thermal equilibrium? When they are in thermal equilibrium. What is thermal equilibrium? If you've got 2 objects touching each other, there will be heat flowing from one object to the other one. Let's say this is 18, this is 20. Temperature. Heat will flow always from the hotter to the cooler one. When heat flow out of A to B, this one will drop. Maybe drop to 50. At the same time, the 20 will rise. Rise to same, in the end, they will always achieve same temperature. When they achieve this state, we call it equilibrium. It is when the heat transfer from A to B is the same rate as the heat transfer from B to A. Doesn't mean that there's no heat flow. There is heat flow. It's just that the rate is the same. So that there's no net heat. No net heat flow. Now, this is the meaning of thermal equilibrium. Okay? When they are in touch long enough. It's the same reason why you enter a room, you feel cold at first. You sit for half an hour, you don't feel cold anymore. Because you're already in thermal equilibrium with the surrounding. Okay? The same reason. Okay, so I mix these two. In the end, you know, they're going to achieve thermal equilibrium. They're going to come with the same temperature. They're going to achieve one temperature. How can we calculate that temperature? Okay, you're going to need this equation. Okay, so now question, when I mix this with this one, who is the one transferring the heat and who is the one receiving the heat? The hotter one is the one that gives the heat. And the cooler one is the one that receives the heat. So when you mix, the heat is going to go here. This is the Q. Just like this. Okay, so we're going to start with heat release. Heat release is going to be equals to heat absorption. Conservation of energy. So assuming there's no loss of heat, so we assume what? We assume all the heat from here is going to go here. No loss. Okay. So what is the heat release? Heat release, now you can do something like this. This is your 50 gram at 100 degrees Celsius. You're mixing with 200 gram at 10 degrees Celsius. When this one give out the heat, its temperature will drop to certain temperature T. This one release the Q, releasing heat, right? The Q is then absorbed by this thing, the other water. So it will rise by taking in the same Q. It will rise to the same T like this. This is how you visualize it. Okay? Again, first one drops by releasing heat. And then this heat goes to this one. Then it absorbs and rise. In the end, they achieve thermal equilibrium. So we can start by writing this Q1, this Q2. Q1 equals to Q2. So M1 C1 delta T1. So that equals to M2 C2 delta T2. M, okay, 0.050 in kg into specific heat capacity of water, 4200. And the change in temperature, now the change in temperature, we just take bigger minus smaller. We just always take the bigger minus smaller. We're only interested in the difference. 100 minus, we know T is going to be smaller, right? 100 minus T. Okay, so just bigger minus smaller, then you will not get negative numbers. You don't have to deal with the negative numbers as long as you know this is heat release. Okay, equals to M2. Okay, 0.2 into 4200. Change in temperature again, bigger minus smaller. So the bigger one, T minus 10. T minus 10, bigger minus smaller. So both sides doesn't have a negative. You don't have to deal with that, right? Because sometimes in chemistry, when you do heat release, there's minus Q. Okay, we just simplify it like this. Okay, so as long as you know your left hand side is the heat being released, right hand side is the heat being absorbed, and numerically they are the same. Okay, so cross. This one time open the bracket, 5 minus 0.05 T equals to 0.2 T minus 2. Okay, so 5 plus 2, 0.2 T plus 0.05. 7.25 and here is okay, it's about 28 degrees Celsius. Okay, that's how you find it. So in the end, these two mixing, they will reach 28 degrees Celsius. So remember, our calculation is assuming that there is no heat loss, right? So we can say the Q1, the release one, is equals to the absorbed one. What happens if you have loss of energy? Then this equation is going to change a bit. It's going to change to Q1 equals to Q2 plus Q loss. The heat released by the first substance is equals to the one absorbed. And it doesn't absorb 100%, right? Some goes to loss. So the equation becomes like with heat loss. So you need to calculate that. Okay. Yes. So first example of the specific heat capacity. Your calculation will always involve mixing this two bodies, sometimes even three bodies. In this case, it's two bodies exchanging temperature. Sometimes maybe they can say this water and with the beaker. So some heat will go to the beaker also. Okay. Some heat will go to the beaker also. So maybe you have third Q, this one is the Q beaker. Okay, some heat will. Right. So that's SHC. Now, then we have, let me bring this a bit here. Okay. For the rest of the guys. Okay, specific latent heat. You got two. One is fusion. One is vaporization. Okay. Now, the easiest way to think about this is you paste your melting curve, your heating curve. How does your typical heating curve look like? Temperature, degrees Celsius. Okay. Am I going too fast? Is it too fast? No, not too fast, huh? Okay. All right. So temperature against time. So let's say what's your typical graph of the heating? Increase, flat, increase, flat. Increase. So let's take water. Let's say pure water. So we know pure water, the 0 is the melting point. The 100 is the boiling point. Okay. Easier, I start here, I don't start at the x-axis. So here is your flow stages. A, B, C, D, E. Okay. What is the state? If I ask, what is the state of the water at point A? What is point A? Point A is like minus 0 is here, ma. So here is all minus, ma. Okay, here is all minus. So at A it could be ice. Yeah, ice, ma. A is ice. It's under the freezing point. From A all the way to B is ice. At B is still ice. Because imagine you heat it, you heat, the temperature increase, rise, and then just hit 0. When the temperature just hits 0, it doesn't turn into liquid immediately, right? It's still ice. Then it starts to melt here. That's the flat line. It starts to melt. So in the middle, you get a mixture. You get a mixture of ice and water. Like at point C is when the melting is finished. So you get all water here. Then you heat it, increase temperature, okay, 50, 60, 70, 80, 90, 100. When you reach 100, it's still water first. Okay, you go from 99 degrees Celsius and 100, you don't turn to gas immediately, right? You still water, and then you start boiling here. Then this is water plus gas, a mixture of both. And then in the end here is all gas. This is your heating curves. For water, for different substances, it's going to look different because of the melting and boiling point is different. Okay, now from left to right, here's a question: is heat being supplied from left to right? Look at the graph. Looking from left, when time is 0 and over time, is heat being supplied? Going from here. It is, right? Because you can see the temperature. It is a heating process. Heating process, I always apply the heat. So heat is constantly supplied. Okay? Even when it's melting, you see the flat curve. Notice the flat curve, the temperature doesn't change. Okay? The flat curve, temperature doesn't change. Does it mean that I'm not supplying heat? No. I'm still giving it heat, but how come the temperature doesn't change? Because in this point, the heat supply is used to break the bonds. Heat is used to weaken the bonds. Because you want to change ice to water, you weaken the bonds. So heat is still supplied. Same here, flat line. Does it mean heat is not supplied? No. Heat is also supplied. So, but it is used to separate the molecules completely. Notice this line is longer than this line. Means more heat you need. Why? Because to go from liquid particles to gas, you want to separate like this. Gas very far, liquid still very close. You want energy to move it separate completely. So it's going to need more energy here. From solid to liquid, you only need to make it loose like this. Okay? Solid particle, liquid particle like this. But you turn it to gas, you need to separate completely. That's why more energy is needed here. Okay? So look across here. From A to B, is there change in temperature? Yes, from A to B, there's delta T, right? So we're going to apply Q equals to MC delta T. Here, where else? C to D, there's change in temperature. So we're going to apply Q equals to MC delta T. Where else? No more. So this is the two sections that to calculate the heat supply. You use these two formulas. From B to C, there's no change in temperature. You cannot use this formula. You will get 0. So we're going to need Q equals to different one, ML, fusion. And the last one, this is Q equals to ML, vapor, vaporization. We calculate it. this one plus this plus this plus this is the total energy you need to go from left to right. Okay, so this is your latent heat of fusion, latent heat of vaporization. So what is really latent heat? So latent heat is the heat you need to break the bonds, to weaken the bonds. Latent heat of vaporization is the heat you need to separate it completely. But in the definition in the textbook, they don't say to break the bonds, right? They say the heat you need to change the state. Same thing. The heat you need to change the state. The heat you need to change the state. What about QMCT? The heat you need to increase temperature. The heat you need to increase temperature. Okay, so specific latent heat is thermal energy needed to change the state of 1 unit mass of substance. This is your meaning. Okay, so finishing up this one. Now, here are the two experiments you use to find specific latent heat. From your formula, Q equals to mL. If I want to find the specific latent heat, the L, Q divided by M. I need to measure what's the energy you give in, what's the mass you have turned into gas or liquid. If you let's say you want to measure LF, fusion, then you need to know how much energy you put in and how much mass of solid you have changed into gas. You got this. This is done by here. So I put heater, melt the ice. The ice is continuously added to make sure the heater is immersed with ice. Then you see droplets. This is melted ice, right? Melted ice. So turn on the heater. From here, you can calculate L equals to Q over M. This is what Q is the energy, heat energy supply. How do we measure the heat energy supply? Electrically. Electrically, Q is here. Power is energy over time. So power time is electrical energy. Electrical energy I supply is the heat energy because energy can be converted. So electrical converts to heat. Basically, this E is the same as Q. This is the same as Q. So I can write PT. Power of the heater, how much time you heat it for, divided by M. Okay. I can even write power in electrical is IV, IVT over M. Okay. So I can measure the I, no problem. I can measure the V, no problem. I can measure how long I heat it for. Then what about the mass? This is the melted ice. How much melted ice here is how much I have melted. I have changed the state. Then you can get your latent heat of fusion of the ice. What about this vaporization? Instead of melting, this is boiling. So equation still applies. LV, latent heat of vaporization, is IVT, same thing, IVT over mass. So I, V, time you heat it. What about mass? The mass is the amount of mass that has turned into gas. How do you get that? How do you get the amount of mass you have turned into gas? Initially, you get mass M1, initial mass. Then this one has boiled. Water decreased to here. Then you get final mass MF. This is going to be bigger than this one, so you minus it. Initial mass minus the final mass. How much mass you have initially, how much mass you have left. That is the amount of liquid that has turned into gas. Right. So the delta M. This is the amount of liquid turned into gas. This is your boiled, vaporized liquid is flowing here. Okay? So for the heating curve, if I make the curve sloping less like this, let's say I compare with another one that is like this. What can you say about the difference? What can you say about the difference? First thing, notice that the flat line is lower. Let's say this substance A. This substance B. Who has a higher melting point? Substance A has a higher melting point now, because the flat line is higher now, higher boiling point as well. What about if I ask who has a higher specific heat capacity? What do you think? Which one has a higher specific heat capacity? Let's say I supply the same amount of energy to them. Okay, the heater I use. The heater gives me a certain power. How many watts? 500 used to heat these two things. Okay, now this is how you see it. Just pick one box. Just pick here. This duration T. Same duration, right? Whatever the duration here is the same. So the heater I use to heat them is the same. And the duration I heat them is the same also, T. That means the energy they get is the same. PT. Same P. Same T. So the Q they get is the same. But this one has a higher change in temperature. This one has a lower change in temperature. So who has a higher specific heat capacity? QMC delta T. This is the same for them. Mass is the same. So this is inverse. Right. Take this one. The one with the lesser increase in temperature is going to have a greater specific heat capacity. Right? Because the Q I give them both is the same. Heater, same. Time I heat them is the same. So Q is the same. So this is the inverse one. The one that has a lower temperature change means it has a higher specific heat capacity. The red one will have a higher specific heat capacity. So the higher specific heat capacity is less gradient, okay, than the lower one. These are the questions